Okay, we've been talking about exponential growth and exponential and logarithmic functions. And this topic is kind of a tweak of the exponential growth. It really fits some real life situations better than exponential growth fits. And this applies to situations where you have a finite amount of people or a finite amount of space. You have a resource or a number that you can't go over. This is the number of Americans who have been have at least one dose of the vaccine for COVID and two doses and a booster. And you can see they all have a shape that kind of starts out exponential. If you look at these graphs, they all start out with this pattern of starting to get steeper and steeper, kind of easing their way in. But then, as you would expect with a finite amount of people, there's 300 and something million people in America, you can't keep that growth forever. So let's focus on the darker green section. There's a certain percentage who will never get any vaccine, but if you take those people out, we have a limit to how many people can, and it levels out. And this is what we call logistic growth. And so that's what we're going to talk about in this video. How do you create an equation that models growth like this? It's a version of exponential where it starts out exponential, but then it levels off. And to be honest with you, I made this same video about 2 years ago when we got sent home for the pandemic. At that point, what I knew was about 20,000 people in America had tested positive for COVID. So at the time, I made a video about logistic growth, and we had something that looked like this. And I thought, all right, best case scenario, this thing really calms down, and it levels out because it was still growing steeply at that point. And I was thinking, all right, so let's say, all right, best case scenario, this thing levels out, and only 40,000 Americans ever test positive for COVID. And that number, I think, right now is in the hundreds of millions. So that prediction didn't work out. But the point's still good. At some point, something that looks exponential has to level out. Right? If every single person in the country got the vaccine, this graph still has to level out at some point. So let's talk about some patterns that start exponential but then level out. And again, this is called logistic growth. All right, so I've taken that graph and I put it into Desmos, and I graphed an exponential, and that's pretty good for a while. So we're really close to that green line for that portion up until, I don't know what date that is. Anyway, sometime in 2020, I guess. So the exponential function I matched to it was really good, but it has to level out. And the thing about an exponential function is, which is good when you're talking about your retirement fund and stuff like that, it gets really steep and it never turns back around if it's really exponential. So what we needed to do was find a graph that looked more like this. It's not perfect, but it definitely follows the pattern a lot better. And I could have probably tweaked it to get a little closer, but we want something that looks like the orange as opposed to the blue. We needed some way to make this equation, just a regular old exponential equation. It's y equals a times b to the x. And that will keep growing and getting steeper. We need something that's going to help it level out. All right, and here's that thing. This is the logistic growth formula. So logistic growth, in order to, it still has a feel of exponential. We still have f of x or y. That's the same y. This right here is our independent variable x. And then we have four constants. We have the number e, the base of the natural logarithm. That's a number we've been working with recently. And then we have these three other things that determine what this kind of S-shaped curve is like. So let's start with L. L is the limit, the max value. That's sometimes called carrying capacity. Carrying capacity. And that applies to like the population of some kind of animal on an island. Let's say an island can support 500 rabbits. You drop some rabbits on that island, they reproduce, and when there's not many of them, they can reproduce quickly. But when that island starts to run out of space and food, um, that number has to level out at some point. That point's called carrying capacity. In other words, how many rabbits that island can carry before you run out of space and food. The other constants are this lowercase k, which is up in the exponent of the e. That is going to determine how steep the curve is. So if you change k, you could change it from something that levels off kind of like that, or you could make it something that levels off like that, gets really steep and then levels off. They all have the same basic shape, but that k will change how quickly you and how steeply you jump up towards that carrying capacity. And the other kind of thing we can, the aspect of this graph we can point out, this x sub 0. That's the x value of what's called the sigmoid midpoint. You don't always see that term, but what that means, it's kind of like the change in, not really the change in direction, but it's like the change in slope. X sub 0, if you find this point where it changes, it goes from increasing faster to increasing slower. That's always going to happen at half the carrying capacity. Right, if you drop 10 rabbits on an island, they start to reproduce. This would be L over 2, and this would be X sub 0. When you get to half the rabbits, let's say the island can hold 500, when you get to half that value, that's when it's going to start slowing down in a true logistic equation. So really, the L is a specific Y value, your carrying capacity. X sub 0, that's the X value of the turning point, and you should know that that happens at half of L over 2. But other than that, you don't need to memorize this formula, and you don't need to really, you could think about the features of it and kind of understand why it works the way it does, but you don't need to know why this formula is the way it is, like where it came from. You should be able to use it. I should be able to say, how many rabbits will there be in 10 years, and you can plug into that equation. So a couple quick examples, and we'll be done with this one. So I graphed two different equations in Desmos just to show you what I mean by the L and the X sub 0 and all that stuff. So here's an example of logistic growth. So we have 20 over 1 plus e to the negative 2 times x minus 6. So the negative 2, we know, changes the curvature. So I changed it to 0.1 negative, I should say 0.2, and then the other one's 0.1. So the bottom one's a little bit flatter. It takes longer. It's a little bit more gradual. And what else we can see is the 20. Where do you see the 20 reflected? I see that right here. It's my carrying capacity. That's my upper limit. It will approach that line as an asymptote. And what else I see is this 6 right here. So at 2, 4, 6, we see that when x is 6, that's the value being subtracted from x in the equation. That's going to happen at 10, which is half of the carrying capacity of 20. So I just recreated that down here with a 30. So here's the 30. And at 20, because I put a 20 in with the x, that's where I start to change direction and go from kind of concave up to concave down. Those are going to be some important calculus words. That happens at 15 because that's 30 divided by 2. So things you should take from this. There is an equation that will level out. It starts out kind of exponential, but then it levels out. Some things that it could model, like maybe the population of rabbits on an island, the percentage or the number of people in America who have gotten their first COVID shot, or it could be like the spread of a rumor, something like that, where at some point it starts growing faster, but it has to level out because you have a finite amount of people. So it's called logistic, and there's a couple key features of the equation that are reflected in the graph, as you can see with these two examples.